Welcome back. In this session, we are going to discuss about error probability of quadrature phase shift keying receiver system. And we know the architecture of the QPSK receiver. The signal S of t is transmitted by the transmitter, and the S of t may be of any one of the four signals. S of t may be S1 of t or S2 of t, S3 of t or S4 of t. Any one of the four symbols is transmitted by the transmitter, and it is affected by the additive white Gaussian noise N of t. And it is allowed to the receiver, and the receiver is assumed to have two paths. One is in-phase path and another one is quadrature path. Each of which are supplied by the sinusoidal carriers, which are all 90-degree phase shift to each other. And the multiplier is followed by an integrator. Over the time period Ts, and the combination of the multiplier and the integrator is called as correlator. Let us assume this as correlator 1 and let us assume this as correlator 2. And this is the outputs of the correlators are given to a decision device which is comparing the output of the correlator with a threshold lambda is equal to 0. And the outputs of the decision device are multiplexed, and the corresponding binary sequences are coming at the output, or otherwise each of the sequence will have die bit. Each clock we are having one die bit output at the receiver. And we know that the R of t, the signal R of t as the received signal, and this path is the in-phase path. This entire path is the in-phase path. And this is quadrature path. And this R of t is given to the correlator, and the output of the correlator in the in-phase path is R1, and the output of the correlator in the received in the quadrature path is R2. R1 is compared with the decision device. Similarly, R2 is also compared with the threshold in the decision device, and the decision device is taking in favor of 1. When R1 is greater than lambda, then the decision device will take in favor of 1. If R1 is less than lambda, then the decision device will take in favor of 0. Similarly, if R2 is greater than lambda, then decision will take in favor of 1. If R2 is less than lambda, then the decision taken is 0. This is what generally we are having. And we have already discussed the signal constellation diagram of QPSK. In which each of the coordinates are having a magnitude of square root of ES by 2 on all the coordinates, all the axes. Hence, we are having the message point S1, that is S11, S12, corresponding to the binary data 11. Similarly, the message point S2 corresponding coordinating S21 and S22, where S21 is minus square root of ES by 2 intersecting on the x-axis, and S22 is equal to square root of ES by 2 intersecting on the y-axis. Similarly, the message point S3 for the binary data 0, 0. Here the binary data for the second message point is 0, 1. This is the message point is S31 and S32. And for the fourth quadrant, the message point S4 accommodating the point S41, S42 for the corresponding binary data 1, 0. And now let us write the expressions in mathematical form. The received signal can be expressed by R of t is equal to Si of t plus n of t. For the time interval 0 to Ts, and I is equal to 1 to 4, where n of t is the additive white Gaussian noise whose mean is 0 and variance as n0 by 2, where n0 is the power per unit bandwidth. Noise power per unit bandwidth. Now let us discuss the output of the correlator 1. Correlator in the in-phase path is given by R of t is equal to integral over 0 to ts, sorry, R1 is equal to integral over 0 to ts r of t into phi 1 of t dt. We know that r of t is equal to si of t plus n of t phi 1 of t dt. Hence it can be written as integral over 0 to ts si of t phi 1 of t dt plus integral over 0 to ts n of t into phi 1 of t dt. And the first integration says that the first term is the message point which represents the correlation between si of t and phi 1 of t, which is represented by si1, and the second term is the noise term, and it is represented by the noise n. So this is R1, where I is equal to 1 to 4. Similarly, the output of the correlator in quadrature channel is given by R2 is equal to square root of 0 to ts r of t phi 2 of t dt, because this term is phi 2 of t. This term is phi 2 of t and this one is phi 1 of t. So we know that r of t is si of t and ni of t. So this integration is written as si of t phi 2 of t dt plus integral over ts n of t phi 2 of t dt. And here we can consider this as n1, the noise factor as n1. Here the first term represents the correlation between the ith symbol and the second orthonormal basis function, so that it can be represented by si2, and this is the noise term, and it is the correlation between the noise term and the second orthonormal basis function. That is why it is written as n2, where I is equal to 1, 2, 3 and 4, and this is R2. Now the decision device has to compare these four coordinates R1 and R2 with the corresponding symbols. Suppose let me take I is equal to 1. Suppose let me take I is equal to 1. Yes, R1 is equal to S11 plus N1 and R2 is equal to S12 plus N2. Similarly, for I is equal to 2, R1 is equal to S21 plus N1, R2 is equal to S22 plus N2. Similarly, we can write for I is equal to 3 and I is equal to 4. Hence, now due to the presence of the additive white Gaussian noise component, if S11, S12 has been actually or the transmitted vector, but the noise is present in such a way that it will relocate the message point here from here to any of the locations in this space by n1 terms. Either this, if n1 is positive, this point will be the S11 plus n1. That is, this point will be square root of ES by 2 plus n1. Suppose this point will be square root of ES by 2 minus n1. If n1 is positive, it will go horizontally this side. If n1 is negative, this will go horizontally to the left hand side. That is, n1 is negative. Similarly, the same message point will have relocation on the y-axis. If n2 is positive, it will go upward. If n2 is positive, it will go upward, and if n2 is negative, it will go downwards. So finally, if n1 and n2 are positive, it will be located here. So the received value will be located here. R1, R2 will be placed here. If both n1 and n2 are having the positive values. If n1 and n2 are the negative values, it will move here. Actually, it will move here. If n1 and n2 are negative values, it will move here. So the same message point is located in these positions, and it is altered within the region Z1. This is region Z1. This region Z1. If this is within this region Z1, then there will not be any error. If suppose the noise is very much sufficient than the symbol energy, that is the message point locations square root of ES by 2, then it will go to the next coordinate, which will lead to 1-bit error. Because if it is located on region Z1, the decision device in the correlator in phase path will decide in favor of 1, and the correlator in the receiver 2 is also decided in favor of 1. If suppose due to the presence of additive white Gaussian noises, either there is a possibility for moving the message point S1 to either second quadrant or fourth quadrant. If it goes like that, then the decision device will check the region. If the region is Z2 or Z4, it will choose a wrong decision. And in these two equations, R1 and R2, additive white Gaussian noise variables with zero mean hence the outputs of the correlator in phase path and quadrature path are having the mean values plus square root of ES by 2 and plus or minus square root of ES by 2 and minus or plus square root of ES by 2. Since SI1 may have 4 values. Si1 may have 4 values that are all S11, S12, sorry, S21, S31 and S41. S11 is square root of Es by 2. S21 is minus square root of Es by 2. S31 is minus square root of Es by 2 and S41 is plus square root of Es by 2. So Si1 can be written as plus or minus square root of Es by 2 plus N1. Similarly, Si2 can be written as minus or plus square root of Es by 2 plus N2. And if you take the mean for the random variables, if mean of R1 is equal to expectation of R1 is equal to expectation of Si1 plus expectation of N1, and we know that expectation of N1 is 0 and the expectation of this is a constant term, so that we cannot take expectation, and this value is plus or minus square root of Es by 2. So the mean value of the correlator output in the in-phase channel is plus or minus square root of Es by 2. Similarly, the mean value of R2 can be written as expectation of Si2 plus expectation of N2, and we know that the noise is having a 0 mean, so expectation of R1 will be written as plus or minus square root of Es by 2. And both as N1 and N2 are Gaussian random variable, R1 and R2 are also Gaussian random variable. And the decision rules are if S1 of t is transmitted, then R1 should fall in region Z1. R1 should fall in region Z1. If S2 of t is transmitted, then R2 should fall in region Z2. If S3 of t is transmitted, then R3 should lie in region Z3. Similarly, if S4 of t has been transmitted by the transmitter, then the received vector R4 should that is R1. The coordinates R1, R2 should lie on region Z1. The coordinates R1, R2 should lie on region Z2 when S2 of t is transmitted. And the coordinates R1, R2 should lie on region Z3 if S3 of t is transmitted. If S 4 of t is transmitted, the coordinates R1, R2 should lie on region Z4. And region Z1 is the first quadrant. This is in the second quadrant. Z3 is the third quadrant, and Z4 is on the fourth quadrant of the signal constellation graph. And from the architecture, we can say that this receiver is constructed with the help of two parallel BPSK receivers. Hence, we know that the average probability of error for BPSK receiver in the presence of AWGN. In the presence of AWGN channel is given by probability of error PBSK is equal to half into error function of square root of 2 EB by N naught. And moreover, where EB is the bit energy. Hence, but here each of the QPSK, BPSK transmitter is carrying each symbol. That is why we can write the symbol energy ES as 2 into bit energy. That is, the symbol energy is represented by twice of the bit energy. Hence, the BPSK, the average probability of error in of the BPSK receivers in the in-phase channel and quadrature channel are given by PBSK I can be written, that is in phase written as 1 by 2 error function of square root of ES by N naught. Similarly, PBSK of Q can be written as half of the error function of square root of ES by N naught. And now, both of these are independent to each other. That is, the BPSK receivers in phase and quadrature channels are statistically independent to each other. Hence, average probability of correct deduction can be written as, the probability of correct deduction can be written as P suffix C, which is equal to 1 minus probability of BPSK in the in-phase channel and 1 minus the probability of error of BPSK transmitter as a receiver in the quadrature channel. And this is, the first term is the probability. The first term is the probability of correct reception of binary data present in the BPSK receiver in the in-phase channel. And the next term is the probability of correct deduction by the BPSK receiver present in the quadrature channel. And both are same, so we can write 1 minus half into error function of square root of ES over N naught Hence, it can be written as a square minus 2ab plus b square. So we can write 1 minus 2ab. So 1 by 2 will cancel. So error function of square root of es by n naught, and b square will become 1 by 4 error function of square root of es over n naught the whole square. This equation is the probability of correct deduction. Hence, the average probability of error can be written as PE, which is nothing but 1 minus PC. So, if PE can be written as 1 minus of 1 will get cancelled. So 1 minus error function of square root of es by n naught plus 1 by 4 error function of square root of es over n naught the whole square. So the probability of error can be written as error function of square root of es by n naught minus 1 by 4 error function of square root of es over n naught the whole square. For greater SNR, that is es by n naught is very greater than 1, then 1 by 4 error function of es by n naught will have the very least value, which is approximately equal to 0. Hence, the average probability of error is approximated as PE is approximately equal to error function of square root of es by n naught. Now, if And we know that the probability of error in BPSK system can be written as PE, which is equal to half into error function of square root of ES by N naught, and the probability of symbol error in QPSK system, PE is approximately equal to error function of square root of, here I can write it as 2EB. This is 2EB, and for this one it is ES by N naught, which can be written as error function of square root of 2EB by N naught. That means if we plot a graph ES over N naught versus the probability of error, then the QPSK system will have a shape like this, whereas the BPSK system will have the error function which is having half the value of the QPSK. This is QPSK system. This line is for probability of error for BPSK, and this is for the probability of error for QPSK. For the same bit energies used on both of the systems. Hence, the performance of QPSK system by means of probability of error is having a worse performance when compared to the probability of error in the case of BPSK system. So, in the case of probability of error, bit error rate, the BPSK system is outperforming or performing well when compared to QPSK system. If the Euclidean distance between each of the message point between the message points D12, D23, D34 and D14 are equal to square root of 2 into ES. If these Euclidean distance, if the noise values N1 and N2, we can say this as D. If the noise value is greater than square root of ES and noise 2 is greater than square root of ES, then the probability of error occurrence will be there depending upon the value. But this may not happen always. So by extending the Euclidean distance as far as possible when compared to N1 and N2, then we can reduce the probability of error. These are all the conditions for erroneous deduction. So the Euclidean distance, if d is large, then the probability of error is small.